What is up, most distinguished patrons of this channel? For today's video, we're going to be diving into part 2 on how to weld stainless steel with the TIG process. If you haven't seen part 1, link in the description, probably watch that first so you're all on the same page, because we're going to be skipping over a lot of what was covered in part 1 in this video, and we're going to be primarily focusing on the welding aspect of this material. So with that said, let's get into it. So, a lot of you guys told me that you learned a lot in the part 1, and that's great. That's why I make these videos. In this video, we're going to be focusing more on the welding aspect of it. And the truth is just like I said in part 1, this stuff welds very similar, basically the same as far as technique goes. For the most part, is just normal steel. So if you have not mastered steel with TIG, you probably should do that first before you go and try and practice this. I mean, I get it though, you know, you might have a stainless repair job or something that you want to weld up and you maybe not be the best at steel, but hey, whatever, it is what it is, right? One of the most important things about welding this stuff is you really need good gas coverage, and I talked a lot about that in the first video, but one of the things I didn't cover was how much the actual welding joint that you have matters as far as what size cup, what stick out, and all of that. And a great example would be this super thin sheet metal here. This, generally, you're going to need a fairly big cup in the flat position because nothing is trapping argon. When you go and weld, say, a fillet weld or a T-joint, where you have the plates like this, your cup being down here in the corner more or less forces argon out and protects the weld a lot better because it's trapped. Remember guys, argon is heavier than air. Therefore, if you have some method of trapping it, you can get by with a smaller cup typically. And I'll demonstrate later, but I'm going to weld this with a number 12 cup and a number 8, and you're going to see that you don't necessarily need a big monstrous cup. What I find is, if you're doing flat position welds like this, outside corner joints are probably one of the worst, where you're welding like this and the outside corner splits the argon flow, or say round roll cage tube or something like that. Having a bigger cup tends to be a must-have. For lap welds, generally speaking, you can get very good results. Same thing with fillet welds with a smaller cup. Honestly, it's probably always best to err on the side of caution. I generally weld most of my stainless with a number 10 cup, maybe a number 12. I tend not to use bigger cups than that simply because the argon coverage isn't necessarily better, and oxides on the surface aren't really a defect until you really get into that dull gray cooked. And this stuff simply isn't like titanium, where the oxide layer is a demonstration of basically material failure. It's already questionable when you see that stainless is not in the same ballpark as like titanium. Anyways, to get started here, what we're going to do is use this piece of scrap stainless that I got, which is pretty thin, probably 20 gauge, 22 gauge, somewhere in that ballpark, and I scribed lines on this. And what we're going to do is just start by doing 1 to 2 inch welds until we make it end to end on this. And then we're going to take a look at the first one. Alright, I completed a bunch of welds and they went from terrible to pretty decent. So let's look at what the differences are and talk about that. Let's start over here. Now, if you're new to TIG welding stainless steel, especially on thin stuff, this is probably the welds that you're going to be putting down. And there's a lot of things wrong here. One, the argon flow on the number 8 cup I was using was pretty low. It was around 17 or 18, so that's not doing any good. You should be up around 20 to 25, maybe even 30, depending on the cup and the gas lens. If you're using a collet body, this is probably about the best you can expect with a collet body number 8, and not really any better. You have to really use a gas lens with this stuff to get proper flow and shielding. Anyways, this was done at 50 amps, so the amperage is a bit high. The gas cup, honestly, a number 8, number 10 would have worked better. The flow was low, travel speed was a little bit too low. Everything about this is wrong. One of the things that you really should notice here, how it has like a V taper where there's a line down the middle. Anytime you see that, that's an indication that you have a lot of penetration, aka melt through, into the back of the material. Generally speaking, on thin material, that's not a desirable thing to see because you're only typically one pass welding this, and you more or less have a thin spot down the middle where it's likely to crack. If you were to TIG weld up a set of thin wall stainless headers and you had this on every weld, odds are it's going to crack right through there. So you want your bead to be on top of the metal, not sunk in this far. Now, one of the things I did do right on this is, if you notice at the termination, the end of every weld, how it's more or less silver gold, especially down over here. I'll move that so you can see it. That's a good sign. That means that I'm holding my post flow there long enough to where as it cools, it doesn't react with the oxygen and form oxides. And you need to be in a habit of, when you start, you get that molten pool established, and then you start moving immediately. And at the end, you want to hold that post flow there. Don't just snap out of it or lift it right away. That's going to get rid of this, and you're going to have oxides and possibly craters over here, and it's going to likely crack. Also, you want to keep your filler rod in the argon shielding. It's a very bad habit with this material, and even worse with titanium and other more reactive metals, to where when you dab with your filler, you got your tungsten here and you dab and you pull this way out of the molten pool where the gas coverage isn't on this. What'll happen is this will oxide, and that oxide will wind up in your molten pool every time you dab it. So keep that filler rod right in the gas coverage. A good habit to be in, if you know that that's contaminated, switch it in your hand quickly and start feeding the other end that should be clean in order to keep that oxide out of there. So I started making changes on these 3, since these first ones I knew simply weren't working, and we have to make changes to get different results. For this guy, I just tried to move faster, and it really didn't result in any kind of net benefit. Again, I'm using a fixed 50 amps to weld this, so I did not vary the amperage to try and control the puddle. This guy right here, I dropped the amps to about 45, didn't like what I saw. This guy right here, I ended up upping the argon flow to 30 cubic feet an hour and settling at 40 amps. And you can see how everything is already starting to look better. The red is not really a defect. It just means that it was fairly hot when it was exposed to oxygen. But we no longer have that melt through. We no longer have that V-taper line that's undesirable on thin material. This is starting to get to acceptable. If you were to take a brush and clean this, it would likely clean mostly up, and it would be pretty good on thin material. So I decided to take the settings that were used here and clamp a copper bar on the back of it in order to see what would happen, and this is the result. So all the settings were the same from this to this. This clearly is a bit colder, and that's because that backing bar, this copper. Now this thick copper backing bar was mostly behind this. This thing started to warp, so it wasn't quite touching, but it did make the weld overall colder. Not perfect, but again, a little bit cleaner of results than this guy. Now this guy is what happens when you use a big gas lens without the insert in it. I didn't notice that that insert wasn't in there like it should be, like on this one. So guess what? The gas shielding once again was poor, and it's all oxide. It has a really weird profile, so be smart about it. Make sure your screen is in it. Now this final one here is pure silver, and that's because I use 40 cubic feet an hour with this big number 14, I think it is, or 16. It's a big cup, And you can see, because this whole thing was covered with argon very well, that it never had a chance to oxide, and it looks a lot better. Now, the interesting thing with all of these is, for the most part, like this, not so much this, but this, they're all acceptable welds, and you're going to have a very hard time on thin wall stainless getting pure silver welds without a ton of argon coverage. In most cases, it simply isn't necessary to achieve that, but now you know how critical argon coverage is for getting results. Now let's take a look at the back. So as I suspected, and as you probably suspected, the backside of all of this is oxided really bad. And that's going to be typical because we weren't running a back purge of argon to shield this, or something like solar flux, which, by the way, I'll have a whole video on solar flux coming out. I bought some and I'll show you how to use that. But we have pretty bad oxide layers back here. Even where I tried to clamp this to this copper bar, because it wasn't in full contact with it, which is typical on thin material, it's going to warp and pull off of it. Even that has pretty significant oxide. The copper bar or backing bar, quench bar, whatever you call it, typically works better on outside corner joints and things on thicker material. On thin stuff like this, it can be an uphill battle to get adequate contact to where it works. So the question is, this oxide layer, is it a defect? Well, yes and no. It really depends on the intended use. This is exactly what the internal welds are going to look like on anything that you don't back purge that's thin, and on thicker material it may end up looking like this, although to a lesser extent. This does not have any corrosion resistance. Therefore, if rust is an issue, or say it was a piping system and all your internal welds look like this, and you put some kind of corrosive material in that pipe, it's going to potentially eat right through this into the weld, weaken the weld, and you could have a failure. So again, it really depends on what you're building. A dump truck box for a salt truck, does it matter? Probably not. It doesn't, it's not going to rot the box out any faster realistically. But again, for high liability stuff, this is undesirable. Now, probably one of the best examples of when this is something you really don't want that people overlook, and I said it in the first video, I'll say it again. If you're building stainless steel car headers or like turbo manifolds, having this crap on the inside of the pipe is not good. As that pipe experiences thermal changes from being super hot to cold, along with all that vibration, this is a great place for cracks to start, propagate from. In my experience, for thin wall tube that's used to make turbo headers, you will have weld failures and cracks if this is what the inside of your weld looks like. So again, it's all in what the use the weld is going to see as to whether or not this is acceptable. So now I'm going to take what we learned so far. I'm going to use this bigger cup with 40 cubic feet an hour. I'm going to use that reduced 30 to 40 amps. And we're going to make a weld on here with that chill bar in contact with it. And we should get an end result that's going to be more or less light straw to pure silver with a better backside of the weld. Again, like I had said earlier, on flat position welds like this where the argon can just spread out, using a bigger cup generally nets better results, but on a fillet weld, you don't necessarily need something this big. So I tried to run this with a backing strip, and almost immediately it pulled up and warped over the backing strip to where it wasn't really touching it. It might have been touching it here a little bit. You can tell because it's a little bit cleaner, because this was run at the same amperage, same speed, and the fact it got clearer here, lighter in color, tells you that it probably had something pulling the heat out of it. This is about what you would want to see on this thin a material. There is some reinforcement up over, especially here, and it's not sunk in. You don't have that dreaded line that's telling you you have a thin spot. The overall weld looks really good. The blue color will clean right off with a brush, and you should maintain most of your corrosion resistance with this weld. So overall, this is very acceptable. I decided to drop the amperage. This was at approximately 30 amps. I dropped the machine down to 25 amps and did this weld. And this to me looks a little bit cold. It's super narrow, it's super high. However, there is some penetration out the back. So overall, this would be acceptable. And it's kind of mind-blowing on this thin a material how 5 amps can make this much of a difference. This was very sluggish to get going. You can see how cold this section is. I had to slow my travel speed, but only 5 amps difference between these two, and the beads look completely different. So this realistically would need to be welded somewhere around 27 amps to get, I guess, ideal for a bead on plate. Keep in mind, if you're welding two pieces of stainless together and not just a bead on plate, you're going to need more amperage. And this is definitely a case of thin material needing a very good TIG welder. When you get into a lot of the cheaper Amazon special TIG welders, many of them only go down to 20 to 30 amps. Therefore, achieving this kind of level of a decent weld without melting through excessively is going to be rather difficult. So it really is machine dependent. If yours doesn't go down low enough, you might be stuck getting results closer to something like this over here. Simply because you can't control the heat input. Doesn't mean that's a bad weld, but again, for the best corrosion resistance, you really want to be into something like this. So now let's look at two welds done in slow-mo. The top one is going to be a number 14 cup with 30 cubic feet an hour of flow. The bottom one is a number 8 with the same 30 cubic feet. So it's not just gas flow that matters, but how that's distributed. The flow coming out of the bigger cup is shielding everything a lot better. And the molten puddle is very clean, very crisp, very round. When you look at me dabbing the filler in the lower one, you can see it almost looks like mill scale forming on the surface. Also note that the lower one, I'm pulling the filler rod out of the argon shielding. That's contaminating and oxiding the tip of that filler rod, which is then being introduced into the puddle. But despite both of these being run at roughly the same travel speed and amperage, the puddle looks completely different. The weld looks different as it's solidifying. Everything is not good on the bottom one versus the top. Now, both of these welds, when they were finished, had a decent look to them, but just the bottom one, the way it welded, was just sluggish and it didn't flow out. And keep in mind, this is just a bead on plate. If this was actually welding things together, you can imagine it would be a little bit more rough and it probably wouldn't join together. You might have like points of a lack of fusion. Any number of things can happen. Let's watch that in real time. So let's do a fillet weld together. This is 1/4 inch or about 6.5, 7 mil. You'd be much better off using 1/8 inch or about 3.2 millimeter material. This is wasteful, I guess, because of how expensive it is. However, the nice thing is because it's so thick, you don't have to worry about melting a hole through it. You can really do a lot of passes to this to get experience without cooling it between passes. One of the things you're going to find with stainless is the more heat you put into it, aka the more passes, the poorer it's going to weld, and you're just going to get a crappy looking puddle. So it's in your best interest for practice to either let it cool between passes or cool it in water. Never cool something you welded in water that actually needs strength. You will actually affect the solidified weld. However, for practice purposes, it's all right. Now I'm going to switch my setup to just use this more or less jumbo number 8, simply because that stubby gas lens just isn't going to cut it. Amperage wise, because this is so thick, somewhere between 120 and 140 amps is what I would recommend. And we're going to use probably 140. So I made 2 welds. This one I did as a partial 2-pass, so I did like a root pass and then capped over it with a weave. This I just did a single pass. Now, I gotta say, it's a real pain in the butt to film this stuff while I'm welding it. I had to do some pretty wonky torch angles in order to get the camera into where you could hopefully see that. So definitely wasn't the most steady doing this. Anyways, even though I ran 140 amps on this, you can see the color is what you would expect out of a very clean TIG weld, which is basically a light straw to pure silver. And 100% that's due to 2 reasons. One, despite running a number 8 cup, the fact that the argon's heavier than air and it's more or less trapped in here means that you have a really good argon shielding, therefore it doesn't react with oxygen. I also had a little bit longer of a stick out here, which if you can see where the tungsten and the arc would be, you're actually covering quite a bit of area with argon shielding despite the fact it's a small cup. Now the other main reason that this looks better than the thin sheet metal is simply because of the heat sink factor. These things have so much mass that it pulls the heat out of the weld, therefore you don't get the level of oxidization that you would find with thinner stuff. And that's why, like I said earlier, using the big cups and different tricks like chill blocks really matters a lot more with the thinner stuff than it does with this thicker stuff. Now let me rotate this guy right here, it's still hot, and you can see there's basically no sugaring on the back side of here other than this tack that I just did a blast tack on to get it over with fast. But that's, again, because this is so thick, you're just not going to get the reaction on the back. One of the things you guys got to understand with this material is it's a very poor conductor thermally speaking compared to steel and even aluminum, but we'll compare it to steel. And because it's a poor conductor, it actually takes a long time for thick stainless to get hot on the backside to where it would react with oxygen. Therefore, on thicker stainless, it's generally a lot less critical to have a back purge. No doubt, if I were to break this, there's some level of oxygen contamination underneath that, and I will do that in a second just to see. But it probably won't be that bad, and realistically, from a strength perspective, it's not going to be a detriment, I don't think. So I broke the plate in half and I forgot how strong TIG welding is on stainless. This actually took a lot of force despite the weld being undersized for the material. But looking at this, I don't really see any evidence of sugaring underneath this plate, anything that would make me question that there'd be a strength related issue. Now there is not much, if any, penetration on this, and I wouldn't expect it. When you weld stainless steel properly, aka like in this case 140 amps, and you're moving fairly quickly, you simply don't have the dwell time to get a lot of penetration, and that's perfectly fine. You don't want to go so fast that nothing fuses and just say lay wire and just go super fast. So it pays to like do a brake test like this just to see where you're at. If you see that original edge of the plate completely unbroken down, that's probably a good sign you're not using enough heat or you're moving too fast. Based on what I see here, the weld is 100% clean. The original plate edge here was broken down. There's, again, not much penetration, but everything looks good start to finish. This would be an ideal result. Going back to what I said in this video a little bit and in the first video, this oxide layer really isn't a detriment, and you can generally clean it off with a stainless steel brush. Now, this is a very filthy stainless steel brush, and don't be an idiot like me. Get a new stainless steel brush and use it. Don't be using ones that are carbon steel or used on steel, because guess what? This BS is going to embed into here and then it'll rust in the future. So use a clean stainless brush. But to prove a point, let me clean this. And you can see with just a little bit of brushing on there, most of that oxide layer is already removed. Now they do make like electrolysis cleaners that will clean that all off instantaneously. And you could always use pickling paste as well, or some form of acid to clean that to where that surface is not going to rust any more than a base material. But you can see that it's really not that hard to produce very clean silver welds on something like this, especially thicker material. Before we go to conclusion, I want to give you guys a bunch more tips that should help you out get better quality welds on stainless. The first one is dealing with lap welds. If you find yourself welding lap welds a lot, or you have one that you need to do and you need to have no sugaring and aka very clean, very good looking weld, it can be pretty tricky, because what ends up happening, and it doesn't really matter if it's thin or thick, I mean, if anything, thinner material is harder to get better results, but you're welding this sucker like this and you end up having an issue where the argon gets split by the edge and it flows out over, maybe it sucks oxygen from behind the cup. Long story short, you can't get that real clean, at least decent looking weld, and it's turning gray. Well, what can often help is if you take a piece of angle iron, aluminum, copper, whatever have you, just set it like that, and then by welding this, not only do you have the chilling effect of this pulling heat out, but you also have argon being trapped in there, and you can even bring it closer, and that will help keep that argon right where you want it, protecting that hot stainless. And as you go, you're going to find that you're going to get a lot better looking weld. Another thing that's worth mentioning is the oxide on the backside of a weld. Like on that thin material, that stuff is reacting in that molten puddle, because that molten puddle is basically all the way through the material, and it will influence the puddle on the front side. So by not back purging it, which by the way, I'll have a whole video on back purging, but by not back purging thinner material, it's going to weld poorer on the front side. It's just the nature. On thicker stuff like you saw on this that I broke in that one, it welds perfectly fine. Like the lack of back purge doesn't affect it. But if you're doing open root welding, absolutely. Like that's probably the worst case of not back purging something. Your root is going to go in really rough without that clean gas on the inside of it. All of that's going to get pulled through if you have oxygen in there. So it really pays for certain applications, aka thin stuff, especially tube that's really easy to back purge, that you probably should back purge it. Another very important aspect of stainless is, as you recall, I mentioned that it's a poor thermal conductor in comparison to steel. Well, it also conducts electricity in a lot different way, in my experience, than steel. And it's very common, say you're welding on this bench here, to have a piece of stainless and you're welding it, and all of a sudden it gets to getting the high-speed wobbles where it's rattling and shaking. I even had that happen to me earlier, and I ended up having to put extra weight on it to get it to ground. This stuff, if you have a poor ground, will drive you absolutely bonkers because the piece will start vibrating. You can get weird arc wandering where the arc will wander to one piece and not the other. So it's always in your best interest working with stainless to have a really good conductivity to your ground clamp. Now, in the case of this table, I have my ground clamp on this copper cable down there, and even I was getting wobbling. So on little pieces that you might be welding on your weld table, grab yourself a copper bar and set it on it for weight, or a third hand where you can set it like that. Do something to keep weight on it to where that path of electricity stays consistent, because otherwise it's going to vibrate. And you don't see that with steel, but with stainless being a poor conductor of electricity, it's far more common, and it will drive you nuts. So be smart about that. Get some kind of third hand or a copper bar, or even a couple pieces of scrap just to set on it to help you out. It will make a difference. So the last tip I'm going to give you guys is a word, and that word is patience. And it's something that you must have to work with this material. And what I mean by that is simple. You cannot take this material and think that you're just going to do pass after pass with complete disregard with the material and that it's going to work out okay. Simply put, you need to give this material time to cool. Now, I did 2 passes on this really quickly, and that's because, well, it's 1/4 inch thick and the weld I put down isn't even really that big. It almost would need another pass based on the thickness of this material. But on thinner stuff, I can't stress how important it is that you not go and blast it with a ton of heat and think it's going to be okay. If you see signs that it's running too hot, aka your molten puddle's starting to look filthy, like you have not enough gas coverage, or the puddle's wetting out weird, all those signs that just you're cooking the crap, shut it down, give it some time to cool, restart. I've done quite a lot of stainless pipe welds, and I can't tell you how many times where things start getting a little wonky, and I just say, all right, I'm going to take a step back, 10-15 minutes, come back to it once it's cooled down. I'm going to brush it up really good with a stainless brush to clean up the surface and restart, and it works so much better than trying to fight through it. Even with steel, with TIG welding, there becomes a point where the puddle is just so hot it just welds poorly because it's more or less producing mill scale on the surface. Well, stainless is just more sensitive to that. Now, if you think stainless is bad, at some point in the future, I'll do a video welding titanium, and you're going to find in a short order that that is a Patience Maker 3000, because if you get antsy with that material, you're going to make it junk. At least with this stuff, you'll still have strength if you go too fast and rush things, but just be smart about it. Take your time. Expect it to take longer to weld this stuff to get good results. And I think that's where most people fail with this material. It's really a lack of argon coverage and simply trying to rush it. It's not a material that likes to be rushed. Case in point, this stuff takes a lot longer to cool off. It holds on to that heat for so long that it's very easy to overheat it. So just give it time. Take time to weld this stuff and you'll have a lot better results. All right, let's go to conclusion. So in conclusion, what did we learn today? Well, realistically, we learned that argon, probably argon and argon matters. Seriously though, argon matters with this stuff. You got to have a decent shielding envelope or it's just going to weld poorly and your results are going to be substandard. Now, I will do a whole video dealing with chill blocks and give you a lot of advice on how to set up for better results with that. But the truth is that if you don't have the argon coverage, and if your ability to run a consistent bead isn't there, chill blocks are only going to probably make the problem worse because you got to be careful with them. You can end up getting lack of fusion or limited penetration if it's not consistently touching the material. But anyways, that's for another video. Based on what you saw today, I'm trying to get you guys to understand that this stuff really isn't that hard to weld. If you can TIG weld steel, you can do this. You just have to have patience with it, and you have to have good argon coverage, or your results aren't going to be that good. So the truth is that you should go out and get yourself some stainless to play with. I like it from a scrap bin because even if it's not that good looking, a little bit of acetone wipe down a scrubby or even a flap disc and the stuff welds like brand new steel. It isn't nearly as bad as old rusty, crusty steel is. So with that said, hopefully you enjoyed the video. If you get any comments, questions, thoughts, feel free to leave them. Until next time.